Yeah, so without further ado, please, Marco, go ahead.
Okay. Okay. Thanks, Jeff and Mario, for organizing this seminar. I know that the main interest is in some aspects of generalized Kähler geometry. And just like Kähler geometry, um, you need to know what complex and symplectic geometry are before you can understand Kähler geometry. And so for generalized Kähler, you need to know what generalized complex geometry is. So I'm going to try to give some idea of what it is. So so we have. I'm not going to assume that you know what the subject is. So so we know that we have complex structures. So a complex structure on the tangent bundle of a manifold is an endomorphism which squares to -1. And this so this is a piece of linear algebra data on the bundle of tangent spaces. But what you can do in order to actually before I talk about complex, let me actually talk about a foliation first of all. So a foliation is a subbundle of the tangent bundle. Which is involutive in the sense that if we take the Lie bracket of F with itself, it stays inside F. So we take sections of F would be closed under the Lie bracket of vector fields. And this implies integrability, or you could say this is the integrability condition, which implies the existence through every point of a submanifold everywhere tangent to F. So it implies the existence of a foliation or a decomposition of M into a union of submanifolds S inside M, such that the tangent bundle of S is exactly the restriction of F to S. So we have this one of the simplest possible geometric structures is that of a foliation. So there's one on the screen here from Josh Jordan. It's the foliation of the three sphere by circles. So that is a rank 1 subbundle of the tangent bundle of the three sphere, and that is automatically integrable because if you take the Lie bracket of a vector of a one-dimensional subbundle with itself, it has to be closed. The Lie bracket is just 0. So in general, the leaves of such a foliation would look like a bunch of parallel submanifolds, all of the same dimension. So we have the integrability condition leading to the geometric structure, these submanifolds. Okay. Okay, so that is one of the simplest kinds of geometric structures you could have. Now, on the what if we had a complex structure? So if we have a complex structure on a manifold, an almost complex structure is exactly this kind of endomorphism, and this determines a kind of foliation because we can look for the eigenspaces of I. It will have a plus and minus I eigenspace. These are called T10 and T01, and these only exist inside the complexified tangent bundle. So we have a subbundle. It satisfies the condition that if I take its complex conjugate, which is just called T01, that it has 0 intersection with its complex conjugate. So this is a piece of linear algebra data. You could either phrase it as as one of these one of these endomorphisms which squares to -1, or you could phrase it in terms of the eigenvectors, the eigenspaces. So we have two eigenspaces, T0, T10 and T01, with eigenspaces plus or minus I. And just like in the case of a foliation, the integrability condition is that one of these subbundles is closed. And this will imply that the other one is closed. Note that, so this integrability condition implies, via the famous Nylander-Nirenberg theorem, that that we have locally coordinates of functions of 1/2 the dimension of m functions. Usually we call them Z1 up to Zn. They're complex valued functions, and they have they have the following property, that if we take that T star 10 is generated by the differentials of these n functions. So in other words, you could say that that we get a foliation, in a sense, by the level sets of the z's and of z bar. So you could kind of think that it's not very accurate, but you could imagine that there are submanifolds where where the tangent space is spanned by dz for one of the submanifolds, and the other one is spanned by dz bar. Now the problem is that in order to make sense of this, we would need to complexify the manifold. So our original manifold is really sitting here, and we were kind of imagining that it's sitting inside some kind of complexified version of the manifold. So you could kind of imagine that a complex structure is a fictional foliation of a complexified version of the manifold. So in that sense, they become unified. Foliations and complex structures are somehow very similar. Any question about this so far? So the idea of a foliation is the kind of primary geometric object, which is generalized successively in many ways for all types of generalized geometries. Okay, and then we have something which seems quite different, which is that of a symplectic structure. And that's just given by a two-form on the manifold. This two-form defines a map from the tangent to the cotangent bundle. And we require that this map is an isomorphism. That's the non-degeneracy condition. And so that's our piece of linear algebra data. And the integrability condition is that the differential of the two-form is 0. And we know that this integrability condition implies the existence of special coordinates. The so-called Darboux coordinates. And these coordinates, they enable you to write the symplectic form in a standard form, in a so-called local normal form. So so we've got these three structures. The first two are kind of appears quite similar. The third one seems quite different. Okay, it's a linear algebra on a bundle plus integrability condition implies some kind of interesting geometric structure. Clear so far? Can I ask anything? I
Can I
don't
just ask,
want.
out of curiosity,
Yeah.
like, is this, I mean, this sort of point of view you said of kind of thinking of a complex structure as a foliation on a fictitious
Yeah.
M sub C, is that ever like I mean, I guess it's can be made rigorous locally for sure, I guess. Is
Yes.
that really like a fruitful point of view or?
Yes. You can. This is a. There's a. So the Newlander-Nirenberg theorem can be very easily proved in the case where the manifold is a real analytic manifold. So if you have a real analytic manifold, so in other words, if the transition functions of your manifold are real analytic functions, meaning that you can expand them in Taylor series, convergent Taylor series, if that's the case, then there's a well-defined complexification of your manifold. And in that case, this becomes the complex structures become a subtype of foliations. And so you can prove the Newlander-Nirenberg theorem based on the Darboux, the Frobenius theorem. This is the Frobenius integrability theorem for existence of submanifolds. So if we didn't know about smooth manifolds, C infinity functions, and we only knew about real analytic functions, then the Newlander-Nirenberg theorem would not have a name, and it would just be the Frobenius integrability theorem. And I think that in truth, when Kähler was working on complex manifolds, and when he was working on Kähler metrics, he was taking a lot of inspiration from uh, manifolds with foliations like this. So you see here the main difference between number one and number two is that in the case of a complex manifold, you actually have two transverse foliations, one of them by T10 and one of them by its complex conjugate. So to be honest, a complex manifold is more like a manifold that has two transverse foliations. That's really what it is like. And actually, if you think about Kähler potentials, which generate metrics, that's that's taking an inspiration from manifolds uh, that have two transverse foliations, where the metric is a Hessian metric, where you take a single function, right? If you have a single function and you take d by dxi, d by dyi f, you get this kind of um, you can sometimes produce Riemannian metrics from the partial derivatives of a single function without having any complex coordinates, just having some foliation structure. Anyway, yeah, I think it's a useful way of thinking. It certainly makes more sense of why people in complex geometry tend to use the z and z bars as if they were independent coordinates. And they are, as long as you're working on the complexification space. Okay. So generalized complex structures, they are, so let me just make a Venn diagram here. So generalized complex includes both of these, as well as some other stuff, and it can sometimes connect these together. There's a structure which is called a Dirac structure, which is a generalization of foliations, and that encompasses all of these together. And let's see, do I want to say anything else? Yeah, that's basically the idea, and of course, maybe I should make clear, just so that we know where we're going. If we have a Kähler structure, so what is a Kähler structure? It's an integrable, some kind of integrable Hermitian structure. So what's a Hermitian structure? So it's a linear algebra structure on the tangent bundle again. So we take the tangent bundle, we give it a complex structure, but we also give it a Riemannian metric. So a Riemannian metric obviously defines a map from T to T star by just taking X to G X blank. Okay. And that, if we so and we can also consider a different type of map from T to T star, which is given by the symplectic form that I just mentioned. So we saw, so what I just did was to take a complex structure and put it here, and I took a symplectic structure and I put it here as well on this diagram, and I put a third type of structure, which is this Riemannian metric. This, what is a Riemannian metric? It's a map like this from T to T star, which is self-dual. So if I dualize this, right, if that's the funny thing about going from T to T star, if you dualize, it will go from the dual of this to the dual of this, and that's the same direction, T to T star. So it makes sense to require this. Here we have symplectic, which is satisfies the opposite condition. Omega star is minus omega, so it's anti-self-dual. And we want this to be an isomorphism. So this should be an isomorphism. All of these maps should be isomorphisms. And to be Riemannian, we want a positivity condition, so that if we take the norm squared of a vector, that should be positive. Okay, so for a Hermitian structure, what we want is for this diagram to commute. So a Hermitian structure means you have all three. You have a complex structure and a metric. If you have both of those, you can produce the symplectic structure by just composing I with G. If you have only the symplectic structure and the metric structure, you can produce the complex structure by just composing omega with the inverse of G. And so you have this 2 out of 3 type behavior, that any two of the structures determines the third. And a better way of saying it is that the compatibility condition between the two structures is that when you compose them, the third structure is what it's supposed to be. So in other words, each structure has its own condition. This one, it has to square to -1. So we have linear algebra structures, and the compatibility between, let's say, omega and I is that if you produce I inverse composed with omega, that tensor should satisfy this condition. That's what it means for these two to be compatible. So the compatibility of A and B means that C is what it's supposed to be. So then we have to have integrability. So this is just the linear algebra. What is integrability for this? What does integrability mean? Well, there's several integrability conditions you can require. You can look at I and require I to be integrable based on what we talked about before, this integrability in the foliation sense. We can have that omega is integrable. Okay, we can require both. Okay, that's another integrability condition. That's the Kähler integrability condition. Or you could require, you could be even more, you could be kind of extremely enthusiastic, and you could require the curvature tensor of G to be 0, or you could require the Ricci tensor of G to be 0. And this would be a much stronger type of integrability that goes beyond Kähler. So this would be, some kind of flat, some version of the flat condition on the manifold. Incidentally, if you only require one, but not 2 or 3, this is what we call a Hermitian manifold. And if you require 2, but not 1 or 3, what do you call this?
Symplectic.
It's symplectic, but it has this almost complex structure on it.
Sorry,
I feel
almost
like there's
Caylor. Yeah, sorry.
almost scalar something.
Almost Caylor, yeah.
Anyway, so there's a whole whole tensorial calculus devoted to figuring out these different integrability conditions. Yeah. Anyway, so the model is going to be that if we want eventually to get to generalized Kähler, this is going to be a pair of generalized complex structures. So those are going to be taken from this larger class. I'm going to take a pair of these and a pair of generalized complex structures which are compatible and integrable. Okay, so the task for today is to introduce this green class of generalized complex. Is that okay so far? Okay. Okay, so right. So the definition, let me just begin with this. So definition is that a generalized complex structure is a complex structure on this extended tangent bundle, which is T plus T star, the sum of the tangent and cotangent bundles. It should be compatible with a pre-existing inner product, and it should be integrable with respect to a bracket which extends the Courant bracket, which extends the Lie bracket. So instead of having a bracket only on the tangent bundle, we have one on tangent plus cotangent bundle. So let me just I just want to be absolutely clear about these things. That's the definition. So we're going to have an operator. It goes from T plus T star to T plus T star, and it squares to -1. Okay, and what does it mean that it's compatible with this pre-existing inner product? So there's an inner product there's an obvious inner product, a symmetric bilinear form on tangent plus cotangent, just from the fact that cotangent and tangent pair together. So there's a natural pairing. It's just given by C of y. So you pair these two, a vector in one form, and then you sum the result. And so this structure, this is a non-degenerate, it's a real non-degenerate bilinear form, symmetric bilinear form of signature n comma n. Okay, so it's very much like what you find in like Minkowski metric. It has an indefinite signature. The way you should think of it is that you have the tangent bundle is sitting in here, the cotangent bundle is sitting inside, and those are both null spaces. The norm squared of any vector, of any tangent vector, is 0. So these are null, meaning that the norm squared of any vector in T or T star is 0, because there's basically nothing for it to pair with. You need a one form to be able to pair a vector with. And so that means that the structure group of this bundle T plus T star is really O n comma n. It's an orthogonal group. It's the group of transformations which preserve this metric. So yeah, we'll talk more about this in a moment. But well, actually, maybe I'll just talk about it now. So it's an aside on T plus T star with its inner product. Okay, so let me just talk about this inner product for a moment. A good way of understanding this inner product is to talk about the Lie algebra of symmetries. So the Lie algebra of infinitesimal symmetries of T plus T star with this inner product is SO NN, or sometimes we would, just to be more specific, we could say SO of T plus T star. And these are transformations Tm to itself such that A equal to 0, right? So it's an infinitesimal symmetry of the inner product. And just like you may already know, whenever you have a vector space, a real vector space with a non-degenerate symmetric bilinear form, the Lie algebra of the orthogonal group can be identified with skew-symmetric matrices. So this is naturally isomorphic to wedge 2 skew-symmetric tensors on this thing. And if we write this out, what do we find? We find that there's a wedge 2T, there's a T tensor T star, and there's a wedge 2 T star. Okay. This is otherwise known as endomorphisms of T. And so the structure of the Lie algebra, the Lie algebra, basically the Lie algebra is decomposing because of the fact that the vector bundle we're interested in decomposes. The Lie algebra of symmetries decomposes. And what we see, this is the kind of first important thing to observe, is that the usual Lie algebra of general linear symmetries of the tangent bundle is contained inside here. So what we see is that the usual infinitesimal symmetries of the tangent bundle of a manifold is present inside the infinitesimal symmetries of this metric. And that's not surprising because this inner product is completely natural. It doesn't require any additional choices on the manifold. It's totally intrinsic on any smooth manifold that we would have this metric and that we would have this Lie algebra. Okay, so this is the let's say the traditional symmetry group of any manifold, of a bare manifold.
Can I ask a question?
Yeah.
Is this isomorphism between the Lie algebra and the wedge product? This is only for split signature, or it's
no. I said this because anyone who studied any kind of Riemannian geometry would know that the Lie algebra SON is the same thing as skew-symmetric matrices. So for a Riemannian geometer, this is totally home base material, but it's true for any non-degenerate symmetric bilinear form. And you can see it right here, right? This is basically saying that A is a skew-symmetric endomorphism. If I put this on the other side, there would be a minus sign, right? So it would be saying that the adjoint of A is minus A. Okay, now but the interesting thing is that just by doing this silly sum of t with t star, we get a structure that has more apparent symmetries. We get these we get these bivectors, and we get these two forms, which are acting on t plus t star. So we're going to give these names. We'll call this beta, we'll call this B, and we'll call this A. Okay, and let's just see very quickly how these things are acting. So, for example, so if we want to see how these are acting as symmetries, let's take beta, for example. So if we take t plus t star, we're going to have an endomorphism of t plus t star. So you can write it as a block matrix. It's going to go from t plus t star to itself. And in this component, we should put the part of the matrix which sends t to t. Okay, and that's going to be your traditional endomorphism, A. Okay, but if you put A there, then minus A dual has to go here. And then we can put zeros here. So this will be an endomorphism of t plus t star that will, oh, I'm sorry, I gave the same name A to the full transformation. So actually, let me change this. Let me just call it, it's not important, let's say R. So here we have a usual element in endomorphism of T. Okay, and it acts on T and it acts on T star, and this will satisfy this condition. This condition, it will preserve the natural pairing between T and T star. You can kind of see what's going on, that if you're going to apply A to a vector, right, and then pair that with a covector, that's the same thing as if you had applied A star to the covector and paired that with the vector. So you could either apply A to the vector or to the covector, and you're going to see you'll get these two terms. So this is an embedding. This is how end T embeds into SO T plus T star. Lie algebra embedding. Okay, so this is the way that classical symmetries act on this generalized tangent bundle, T plus T star. Any question about that? I'm going to do beta and B next. There's so many participants, and all of you are silent and invisible. Does anyone want to?
I think it's okay. Or, I mean, this is okay.
Yeah. Yeah, but you're saying it's okay, but it's okay for you. Yeah.
Yeah, well, that's true.
No one wants to talk. We have to, there has to be a, you know, I'm waving the red fabric for the toro, you know, but if the toro doesn't come with the red fabric, there's more drastic things we can do to make the bull come question. Okay, let's do the next one. So the next one is beta, which is in wedge 2t. And look what you can do with that. You can define a map like this. Oops, sorry. We can do a block matrix. And there will be a component of this which takes T star and maps it to T. And so we can put the beta here. Okay, and it will take a vector plus a one form, and it will map it to the interior product of the one form on the bivector, and it will just ignore the vector part. So this is more interesting because T and T star are not preserved. They're not individually preserved by this transformation. You know, if you have a point, if you have a tangent plus cotangent vector, and you apply this beta to it, then it will. Well, actually, this is the Lie algebra element, but let's try to exponentiate it. So this embedding of wedge 2t into SO t plus t star can be exponentiated. So if we exponentiate one of these Lie algebra elements, what would we get? We would get 1, the identity, plus beta, plus 1/2, 1 over 2 factorial beta squared. But if you square this upper triangular, you're going to get 0. So it just terminates after 2 steps. And we just get this. So you see, you get an upper triangular matrix with the identity on the diagonal. And so what that means is that the exponential of beta will take this point and will send it to itself plus a component which takes whatever the covector component of this vector is, and it shears it in the tangent direction. So it moves it in the tangent direction. So exponential beta, it has this this shearing behavior of taking t plus t star elements and moving in the t direction. So the t star is not preserved. It's moved. Oops. It's moved. Potentially to another location within the bundle. So you see that this is a kind of cool aspect that t star is not preserved, but the structure of t plus t star is preserved. The inner product, the orthogonal structure, the metric structure, if you want to call it that, it's not really a metric, but this bilinear form is preserved, even though the individual bundles are not preserved. Notice, however, that T is preserved by this orthogonal transformation. It's basically just a shear. It's a shear which fixes T. Okay, and then finally, let's take B in wedge 2 T star. This is the most important one. This is called a B field transformation. Okay, and it looks like the opposite of the beta. We have zeros here and we put B down here. And what it does is it only acts on the tangent part, but the output is purely in the cotangent direction. And the shear is in the opposite direction. This is the exponential of B. The exponential of B will be 1B1, 0, acting on T plus T star. And all of these are orthogonal transformations. This is in O of n comma n. Okay, so this is really the fundamental thing to understand. This is this big aside here, which continues. This is the fundamental thing to understand, that the playground that we're in is the playground of T plus T star, where the individual bundles T and T star are maybe de-emphasized, and it's really the geometry of the sum that is emphasized. This generalized complex structure this thing has to be compatible with the inner product. So this has two interpretations. You might assume, so you might think, well, okay, what does it mean for J to be compatible with this inner product? Maybe it means that it is an orthogonal transformation. So maybe it means J is equal to, maybe it means this, which is to say that J is an orthogonal element. It's an element that preserves distance. Or maybe it means that it's a Lie algebra element. J plus J is equal to 0. So this is the Lie group version, and this is the Lie algebra version. So which one is it? It's either, the answer is that it's either one, because of the fact that that J squares to -1. So for example, if it satisfies this condition, then I could plug into the second variable J of something. And if I put J of something here and here, then this becomes a -1, and I end up with this condition. So whether you ask for J to be orthogonal, or whether you ask for it to be infinitesimal orthogonal, it doesn't make a difference because of the fact that J squares to -1. So it's a symmetry one way or another. And this is very important in generalized scalar geometry, because you can view it happens a lot that you have a type of structure that you could either view from the Lie algebra point of view or from the Lie group point of view, and you'll do different things with it depending on the interpretation. So that's what this condition means. And then the last thing I need to explain is, what does it mean for it to be integrable? So before I move to integrability, there has to be at least one question.
I have one question.
Oh,
sorry.
Okay, yeah. So now we got two questions, even better. Okay.
The other one first, please.
No, go ahead.
No, one question is why don't you emphasize the special role of the cotangent bundle inside tangent plus cotangent? I mean, you really, even if you're talking about the linear algebra, you have a flag.
I would say that at this point there is no distinction. The distinction comes purely from the integrability side. I don't believe that at the linear algebra side there's any reason to single out T or T star. That only happens at the integrability side, because we're going to see that the bracket is going to be 0 on the T star, and it's going to be the Lie bracket on T. So that's where T is very special. But from the algebra side, it's not. It seems weird, but yeah, it's not symmetrical once we get into the actual integrability condition. Okay, Caleb, I think you had.
my question was essentially the same. I wanted to know why B was more important than beta. But
Yeah, we're gonna
I think
find
you
out
just answered.
in a moment why. Any questions besides this, though? It's got to be at least one more question from all of those invisible, silent, and not from Anna, from one of the students. You're testing my patience. I'm working on my patience. It's one of my New Year's resolutions for 2021, to be more patient. So I'm gonna wait for a question.
Okay, so this is kind of abstract, but I wanted to ask a question. Is there any like interesting Lorentzian geometry to the neutral inner product on like T plus T star? Since you mentioned it's got this like mixed sign, or a mixed signature, like is there anything interesting you can do there? Or
yeah, I think there's a lot. I think it is very interesting. we're going to see. So actually, there's a very good answer to your question, which has a lot to do with where this all started from. Like, where did this idea come from? So this idea kind of arose in two independent places. One of them was in the study of Poisson structures by the Weinstein School, and the other place that it arose was in Nigel Hitchens' work. And especially if you look at where Nigel Hitchens started, he started with something very special about the Lorentzian type geometry of this inner product on T plus T star. That the fact that it's a split signature metric, okay, was the key idea that started the whole subject. And I'll get to that later today. So just keep an eye out for that. Okay, so now the second part of the definition is the integrability condition. Okay, so the integrability condition is just like in the usual complex structure case. So remember that we had this complex structure on the tangent bundle, I squares to -1, and then we took the plus I eigenspace, that was called T10, and then we require that T10 is closed under the Lie bracket. Okay, so now let's do something similar. So we have this complex structure on this larger bundle. We can take its plus I eigenspace, and I call that L. And the minus I eigenspace is L bar. And what we get is that this generalized tangent bundle, this larger bundle, if we complexify it, then it will decompose as the plus I and the minus I eigenspace. Okay. Now, furthermore, let's say that J A is IA. Suppose A is an element of the plus I eigenspace. Then look at what happens if I take the inner product of A with itself. We get, so this is the same thing as if I applied JA and JA, because J is an orthogonal transformation. But A is in the I eigenspace, so this is the same thing as IA. And this, I've just complexified everything, so this thing is still C linear, so I'm going to get minus AA. Okay, so you see that if A is in the plus I eigenspace, then A is null. So what this means is that L and also L bar is what they call, so people use different terms for this. The correct terminology is that it's a maximal isotropic subbundle. And sometimes people use a loose terminology and they call it Lagrangian. Okay, because the inner product restricts to L to be 0. This is nothing too shocking. The same thing is true of T, just like T and T star. Okay, so we have T and T star, and we can also decompose it as L and L bar. Okay, so in a sense, the Lorentzian structure, we're now changing the basis, and we're using the plus I and the minus I eigenspace, both of which are null, and we're decomposing this generalized tangent bundle in this way. And notice that that we could even do the same thing, right? We're going to do this later, but we could even look at the Lie algebra. if we take the Lie algebra of t plus t star, and if we complexify it, this is you could write it as wedge 2 of t plus t star like we did before, or you could write it as wedge 2 of L plus L bar. It doesn't, it's the same space. We're just decomposing it in a different way. Here we're using the fact that there's a generalized complex structure. Okay, so so all of this is just to say that there is a plus I eigenbundle and it's maximal isotropic. The reason it's maximal isotropic, by the way, is just that you can check that if you, for example, if you took the tangent bundle, it has half dimension inside t plus t star, and if you added anything to it, if you added any one form whatsoever, that would have a non-zero inner product with some tangent vector. And so that's the maximum that you could possibly have. It's the maximum null subbundle that you could have for this natural pairing. Okay, and what do we do with this plus I eigenspace? We just require that it is closed under a bracket. We require that L is closed under this bracket, where this bracket is the so-called Courant bracket. And the bracket looks like this. It's the usual Lie bracket on the vector part, and it's you need to extend it. So we're going to let the vector field differentiate the one form, and then we can do the following. So we can do a partial kind of operation IY dec C. So this is, it doesn't look particularly nice. This is not skew symmetric. Notice that the bracket on T star is just 0. Maybe it's useful. Yeah, let's move this over and say some more about the bracket. So it's not skew symmetric. If you take a bracket of x with eta, so a vector with a one form gives you just the Lie derivative. If we check what happens if we take x plus c and multiply y plus eta by a function, then it behaves nicely. It actually is f. And then there's a derivative x applied to f times y plus eta. But this is not skew symmetric. So there's a different law. If I multiply the first argument, I'm not going to get something that is well behaved. What I'm going to get is almost well behaved. So I would have a differentiation like this times x plus c, but there's going to be an extra term, an unexpected extra term, which comes from the fact that this term and this term are different. It's the way that y differentiates c is not by the Lie derivative, but by this half Lie derivative. Okay, and this extra term is going to be like this. This is the very cool thing. It's going to be the inner product x plus c, y plus eta. This inner product multiplied by dg. So this extra term is only in T star because it's the derivative of a function, but the coefficient in front of this dg is the inner product the inner product that we discussed before, this natural inner product here. Okay, so there is, this is a weird bracket the first time that you encounter it. I should also say it satisfies the Jacobi identity. But you have to be careful when you write it because, again, it's not skew symmetric. So it's not a Lie algebra, but it satisfies the Jacobi in the sense like this. A, B, C is A, B, C minus B, A, C. So the adjoint action is a bracket, is a commutation preserving map. So Jacobi is satisfied, and this is an example of, so whenever you encounter something like this that is badly behaved and doesn't satisfy the axioms, you try to give it a fancy name. So it's an example of an L infinity algebra, or sometimes people call it an L infinity algebroid. So basically the idea is, the reason that they call it L infinity algebra, sometimes they call it a Lie algebra up to homotopy. The reason is that all of the laws that you wish that it satisfied, it actually satisfies them if you throw away exact terms. So like this DG term, could throw that away and we would be in a better situation. Okay, and that's it. So we just require that oh, and maybe I should say, what's the failure from being skew? So the failure of skew is like this. It's easy to check. You just take x plus c and you take the bracket with itself. If you do that, then let's calculate that. You have bracket x with x, that's 0, the Lie bracket of x with itself. Then there's going to be the Lie derivative of xi minus ix dxi. And if we write this out, we get, using the Cartan magic formula, remember that Lx is dix plus ixd. A lot of people get through their PhD with just that formula. And what you get here is d of ixc, because you get a cross term that cancels out. And this can be written as d of the inner product x plus c with itself. So take a look. This is an important one. The bracket of vector plus 1 form with itself is exact, and it's given by exactly the inner product. So again, the failure for being skew symmetric is exact. Okay. But I mean, it really is not necessary to know any of this fancy stuff about L infinity algebra at all. You don't need to know anything about it in order to work with this bracket. You just need to be open-minded enough to deal with things that are not Lie algebras. That's all. I think that the experts of L infinity algebras were kind of surprised that this structure even exists. So it's not like we got this structure from these L infinity people. This structure came from, geometry. It's the best explanation for the origin of this bracket is in the work of Pavel Cervera. So Pavel Cervera has these famous letters to Alan Weinstein. And in the first letter, he explains the motivation behind this bracket. And the motivation really is two-dimensional sigma models, topological two-dimensional sigma models. And so from that point of view, it's also clear it makes sense that it becomes L infinity from that point of view. But again, it's really, there's no need to go into all that detail. Okay, and so we just require that L bracket L is in L. Sections of L are closed under the bracket. This is the involutivity, courant involutivity, and that's the remaining. So there's an interesting lemma, a useless lemma, but it's an interesting one to know, which is that courant integrability of the plus of the plus I eigenspace of a GC structure, it actually implies that J is orthogonal. It's an interesting fact, and it's not surprising because of the fact that the inner product is secretly embedded into this bracket, because of these properties. Because of these properties, especially this one, the Courant bracket knows about this special inner product. And so just requiring that it's closed under the bracket is enough to imply that it's orthogonal. So sometimes if I want to save some time, I won't even bother telling people in the definition that that it must be compatible with the pre-existing inner product. You could just omit this and just require that it's integrable. Okay, but that would be, that would be, you would be missing a kind of important piece of information. So, okay, so then let's just summarize.
Could I ask a question about that?
You already did, but go ask a second one.
Oh, I can only ask one.
No, I mean, you asked whether you could ask the question, and I say yes, and you may now proceed. Yeah, I'm just giving you a hard time, Francis. You always ask whether you can ask first.
I was wondering if you have any subbundle that's closed under the bracket, if it's automatically Lagrangian or isotropic or something. Like what's
yes
what?
Yes, there's a general remark, there's a general result along those lines about Dirac structures. Yeah.
And Marco, sorry, this is Dorfman bracket, right?
Okay. So there's a great controversy, right? There's a great controversy in that the original Courant bracket was the skew symmetrization of this bracket. And then I needed to use both of the brackets in my thesis. And so I called this one, I called it the Dorfman bracket. And I gave it a different notation and so on. Okay. So should it be called the Courant bracket or should it be called the Dorfman bracket?
I don't mind either way, I guess. But
yeah. So
I was just confirming, I guess.
The point, though, is this. So there's a reason for this. There's a reason for this so-called controversy or this ambiguity. So the reason is that because of the fact that this is an L infinity structure, because it's a structure up to homotopy, that means that there's different ways of strictifying it in the way they speak. They say, if you have a certain structure and if you want to like realize it on the nose, right, there's different choices you can make. And it's for this reason that we have different ways of deciding, okay, this part of it is the bracket and this other part is, some other tensorial quantity. But it really doesn't matter. Like the point is that at a deep level, there is an ambiguity about what the bracket is. And so they're all the Courant bracket in my opinion. All of these expressions, they're all representing the same information. Sure. And the same thing happens even in the definition of higher structures, like two groups and two algebras, for example. It's always the same problem, whether you want to strictify it. Like, for example, you could say, if you had a Lie algebra up to homotopy, and if you wanted to write it down explicitly, you could either ask for the skew symmetry to hold on the nose, or you could ask for the Jacobi identity to hold on the nose. and you have an ambiguity there, and it's genuinely there. It's not like there is a canonical way of expressing the structure, and that's exactly what's happening here. So that's the reason why I will sometimes write a paper in which this is called the Courant bracket, and sometimes the other one is called the Courant bracket. I know this is not a very wise thing, but whatever. Anyway,
the integrability also is, I guess, is equivalent, right?
It's equivalent. Yeah, it's totally equivalent, because of course, the thing that we're measuring the integrability of is isotropic. And so all of these bad terms, they all go away.
Right.
Okay, and that's a good point that we should put. So there's a useless lemma, but there's a really important lemma. This is I should have said this, like if I had prepared this lecture, I would have said it without delay. I would have said that right away we can see that if L is involutive and isotropic, all the bad terms, all the failure terms, all bad behavior of the bracket vanishes. Right. And we get a Lie bracket. Okay, so so that means that as soon as we have agreed on the definition of integrability, that this plus I eigenbundle should be closed under the bracket, we immediately get a Lie algebra, and that's the first Lie algebra that we see, because the bracket itself is not Lie, and so it's a kind of emergent Lie bracket. Okay, so let's just summarize what we have so far. We have Tm. We have an inner product, which gives the structure of an ONN. And the Lie algebra is wedge 2 T plus T star. We have a GC, so a GC, and we have a bracket, a Courant bracket. This is the initial playground of generalized complex geometry. And this playground is called a Courant algebroid. It's a special case of Courant algebroid. A Courant algebroid is basically a vector bundle. It should have a map called the anchor map to the tangent bundle of the manifold. It should have an inner product. It should have a bracket. This should be bracket preserving, and it should satisfy some laws, like the laws that I wrote above here, this stuff. So this is a special kind of Courant algebroid. I won't go into detail about that. Then we introduce the geometric structure, a generalized complex structure. Actually, let me take the opportunity now to. Oh wait, sorry. I started at 4, and When would you like me to stop today?
Well, it sounds like you're wrapping up. Is that right?
I could stop in either in 5 minutes or in 15 minutes.
Maybe 5. I guess.
Okay, yeah. So let me stop now. Yeah. So the summary. So then we have a geometric structure, a generalized complex structure, J. It's compatible with the inner product, and the plus I eigenspace is involutive. Okay, and I just want to mention what you get right off the bat without any further analysis. So the first thing that you get is that we now have Tm with this inner product and with J. So this now becomes a complex vector bundle. And the complex structure is compatible with the metric. And so that means that the natural symmetry group of this is not ONN, but it's actually UMM. it's like a unitary group because we have a metric, although it's split signature, as well as a complex structure. And whenever you have those two, you get a unitary group of symmetries. And the only way that this can make sense is if n is 2 times m. So it may not be completely obvious, but it's a short calculation that in order to have one of these GC structures, this implies that the dimension, the real dimension of the manifold is 2m. And the structure of the Courant algebroid is reduced to the unitary group, the split signature unitary group. The second thing is that L and L bar get a bracket. So we have this T plus T star, and inside here, usually I think of it as being yellow, we have L. And this L has a bracket. This sections of L has a Lie bracket. And it has a projection map to the tangent bundle, which is bracket preserving because of the fact that the first component of the Courant bracket is the Lie bracket. Okay, and this turns out to be an example, is a nice example of what's called a Dirac structure, or also a Lie algebroid. You can see the pattern. Algebroid is, it really means that it's like a Lie algebra, but it's a vector bundle. So it's spread out over a manifold. So this thing is very similar to L is the direct analog of T10 in complex geometry. Okay, so that's how you define the structure properly. And maybe next week I'll talk about kind of the basic structure theory of this geometry, and hopefully the next lecture after that would be how it should be integrated into GK geometry. So I don't know. I mean, I could easily give 3 lectures, which wraps up those, after this one, 2 more, which would basically cover the basics, if that's what you want.
Yeah, at least. I mean, what else did you have in mind? Or if 3 is the lower bound, what's the upper bound?
Well, I mean, the upper bound, there is no upper bound.
Is infinity? Okay, I imagine that's one.
The upper bound is a hard upper bound of my life expectancy, but
right.
I try to keep fit, but
Right. Well, anyways, maybe we can talk about it. But yeah, in any case, for sure, what you said, at least for the next 2, sounds great.
Okay. Okay. Yeah.
But so let's maybe thank Marco. That's a very nice talk.
And you guys should, if I'm assuming that you've got a bunch of students here, the silent, invisible students who are studying this, and try to get some questions together for next time.
Yeah, sure.
So
well, and maybe I just ask, are there any here at the end? Any more? I actually had just sort of like a hopelessly vague question.
Yeah.
I mean, I guess you, at the very beginning, you sort of said that this kind of thinking of a complex structure in terms of this foliation of a fictitious or maybe not like complexified manifold. I mean, is there something similar for like Dirac structures and T plus T star?
Yeah, that's a good question. I mean, it's related to a lot of things that people in Dirac geometry have studied, like, a lot of the things that, some of the things that people study when it comes to Courant algebroids is, whether you can integrate a Courant algebroid, whatever that means. I mean, in other words, they would like the Courant algebroid, this T plus T star, to be almost like the tangent bundle of some larger space.
Right.
And there's a lot of people who are in double field theory who try to make sense of this and so on. Yeah. But anyway, the point is, it is a very good, it is a they're thinking along the right lines. The Courant algebroid is the symmetry algebroid of some larger space. It is true, and on that space you could imagine having these foliations, and that's what Dirac structures are. But it's you're getting into a territory which is more higher categorical. And so whenever you're talking about something higher categorical, it becomes less, it becomes more detached from real geometry, right? But it's still there. I mean, you can make sense of it. You can talk about gerbs and the total space of a gerb and the geometry on gerbs and stuff like that. But it's, when you start to ask for a concrete geometric formulation of it, like they do in double field theory, you will fail just like they do in double field theory. Sorry, I mean, I know it's being recorded, but that's the problem, is that the thing is there and the intuition is correct, but the problem is to realize it concretely in finite dimension is not something that is really possible in general.
Because I mean, from my point of view, like for this like pluriclose flow, generalized Kähler-Ricci flow, this stuff, I mean, the actual generalized metric is really like the right thing to try to estimate and control and whatever. And
right. But you know how you see those higher symmetries, those higher gauge symmetries, the way that you can take the flow and you can write it in different frames,
right.
The existence of that additional symmetry is it's really a sign of this higher structure. That's the reason why that is happening. But anyway, it's not, we can talk about it more later.
Yeah, sure.
I have a question about what you said of this equivalence between the two brackets when you think of them in terms of like this infinity algebra framework. If you think in terms of groups instead of Lie algebras, I mean, if I think of a two group, the only property that they can lose is associativity, I guess. Or are there others? While here I can choose between like associativity or like between Jacobi or skew symmetry. So I don't know if there are. I don't know what is my question.
No, it makes sense. But the thing is that that's true. But that is exactly the case of a group, right? But if you go to a two group, like in order to get this phenomenon, you need to go to two groups,
right?
And when you go to two groups, you have the corresponding you have the same corresponding ambiguities. So I don't know if there's anything I can really say, but it's because of the two group issue. If you look at a Lie algebra for a group, for a Lie group, there is no maybe a better way of explaining it is like this: is that when an easy model to work with homotopy theory is chain complexes. Chain complexes are easy to grasp. So rather than to talk about two groups and so on, it's better to think in terms of chain complex. If you have a Lie algebra structure on a single vector space, it's clear what you mean. But if you have a chain complex of, let's say, of length 2, and you have cohomology groups, let's say the kernel or the co-kernel, or if you have a chain complex of many vector spaces and you have homology at every location, right? So you could ask, what structure does my chain complex have to have in order so that the cohomology has a Lie algebra structure on the nose, like a genuine, maybe I'll phrase it even more exactly. So you take a chain complex, a cochain complex, you take its cohomology. What do you get? You get a graded vector space. A graded vector space can have the structure of a graded Lie algebra. And that's a very clear law, Jacobi, everything. It's skew symmetric up, with a skew symmetric with a graded Jacobi identity. Now, if you ask what structure does the cochain complex have to have in order so that it induces a graded Lie algebra on the cohomology, the answer is an L infinity algebra. And the complexity and the ambiguity of that structure depends on how long the cochain complex is. So if it's just a two-term complex, there's only so much ambiguity that you can have because homotopies between maps of chain complexes, like if you have a map of chain complex, it goes straight down. The homotopy would go one to the left, but then a homotopy of those would go 2 to the left and 3 to the left and so on. And so depending on how many homotopies you can have in your length of chain complex, that will give you more and more ambiguity, more and more freedom of what the laws can be on the first thing, on the cochain complex. So that's the problem, is that when we go from tangent to an extension of the tangent, it's basically something that maps to tangent, it's something that has an inclusion of cotangent, right? So that means that what you're really doing is you're expressing the tangent bundle as a cohomology bundle of the courant algebroid modulo the cotangent bundle. So E modulo T star is T. So what structure on E do you have to have so that it will induce a Lie algebra structure on T, and it will be a Lie 2 algebra? And then if it was a higher courant algebroid, like you've studied some of those exceptional cases, those are it's a filtration by several steps, and that would go higher and higher, and it would become even more ambiguous as to what the brackets are.
Thanks.
Yeah. Okay. Have a good evening, everyone. I'll put my notes.
Yeah, I guess, would you mind emailing them to me? I'm trying to, I have this website gathering it all together too. Is it okay?
Should I just email it to you?
I mean, yeah, and I can put it on the webpage.
Okay, great. Yeah. Okay, so see you guys next week.
Yeah, thanks again, Marco. Yeah, thanks everyone. Yeah.
Thank you.
See you next week.